So, hi everyone. My name is Mahsa Jami, and I'm a scientist at NASA's DAAC. And I'm very happy that I'm going to talk about the parallelizing code today. So we can dive into parallel processing and kind of learn what it is today. And hopefully you will get enough information that you can dive into that right away. As you all are familiar, many data sets that we are working with, they considered as a big data. They are stored in different data formats, and that they hold several variables in a hierarchical data format. They also have spatial and temporal aspect to them. And there are cases that we want to answer a science question and we only need to open one or a few files. But there are some other times that we need many, many files and we want to do a complex task on that data. And we are seeking for ways that we can make this process efficient and perform our analysis in the most efficient way. So we are familiar with the for loops. That's the way that we can automate the data processing. But the parallelization, it takes it into another level, and it helps us to really efficiently use all the capacity that we have in our computer and do the same analysis. In this slides, we are using a few examples for a comparison. I just added the link here for you so you can reference it back. But technically, we are accessing the high-resolution global sea surface temperature data sets in the example, but you can also access those. So when we talk about the parallel processing and we want to define it, it's good to know what serial processing is. The serial processing means strictly sequential. That means that you have tasks and an object, and you have to be able to perform tasks for an object. You have to go through each task separately and in turn to get to an output. And if you have other objects, you have to repeat that after your process is done for the first object. So when we talk about the parallel processing means that you can do the same thing and get to the same result, but you can do your task simultaneously. Especially if you have self-contained functions and tasks, you can really benefit from parallel processing and save some time. So an example of showing how the serial processing works, we are using a function here throughout all the examples, which is a simple one. It does read the data. The data is the sea surface temperature data from oceanography DAAC, and it returns the time step and a calculated mean for just one layer. So in an example here, we are doing the same process for only one file. And then we are repeating the same thing using only the for loop to automate the task for a 6 file. So it took 20 seconds for just one task to be complete and 1/22 for all those 6 files to go through that function. So that gives you an estimate of how much time you will need to spend if you are accessing more data, let's say for a whole year. So this specific data set does have a daily data set. So a whole year includes 365 data. So you will have a rough estimate of how much time you need for that. But when we talk about the parallel processing, the first thing that we focus on is that makes the process faster. So in the parallel processing, we are using tools that enables us to spread out all the computation to use the full capacity of our computer. So most of our computer do have between 4 to 8 cores, but Python by default only uses one, but the parallel processing led us to be able to utilize all those cores to be able to do the analysis in parallel. And when we think about moving to the cloud, we don't only talk about moving our code next to the data, and we also think about the ways that we can benefit from what is available a lot more than what we have in our computers in the cloud. So that's also a very good consideration when you think even about migrating your processes to the cloud. So we are repeating the same example, but we are using the parallel processing in this way, in this case. So the same function is repeated for one example, and it took 15 minutes this time. And we repeated that for six tasks, and it took significantly less time. So obviously the parallel processing will help us to do the computation a lot more faster. So there are multiple tools that you can utilize when it comes to parallel processing. A lot of them are pretty manual, so they might need a deeper understanding and knowledge of how computers do the parallel processing, and how our computer works to be able to set up that code. So we are going to talk about DAAC today, which is a Python package for doing the parallel computation. So only because it's a Python package that enables you to jump into the parallel processing. And it doesn't really require a lot of deep understanding, and a lot of complicated tasks is being handled by this package. And it significantly lowers the barrier for starting the parallel processing, especially for us scientists. And it integrates well with the familiar geospatial Python packages that we work with them, like pandas, numpy, and xarray. There is a phrase that it's frequently used, embarrassingly parallel workloads, which sounds made up, or perfectly parallel, or pleasingly parallel, which refers to a workflow that includes one process that is completely independent of any other. So it's pretty self-contained. It doesn't need output from other processes. It's completely independent, but you want to repeat that process for many files. So that's a very familiar workflow for us, that let's say you want to do some processing or analysis on one file and expand it on the entire time series, let's say. And next, let's look at how we adjusted the code example that we had to make it work with the DAAC. So there are three main features that are added in this code. One is client. So we need to define a client, and client is technically a gateway that opens the door for us to use the parallel computing. So it depends on the computer that you have, the memory that you have are accessible to you. You can define the number of cores. Technically, that means that how many tasks should be done in parallel for your workflow. So in this case, this example is ran in 2i2c. That's 4 cores available in 2i2c, which means I can do up to 4 workflows in parallel. So the next thing is using this delayed method or function that enables us to use that function and operate that lazily. What does that mean? That means we are not actually doing the computation, but we are setting up a ground and making our functions ready to work with the work in parallel, or do the analysis in parallel. So that's called lazy because it doesn't do the actual computation. And then the actual compute function that runs and actually does the job, does the task, perform the tasks. And when you look at the client and the information, there is a launch dashboard in Jupyter Lab option. If you click on that, that also provides many visualization for us that we can track the progress of our task. So I ran this example into I2C, and this is a screenshot of my work environment. So when you click on that dashboard icon, you can navigate to this DAAC option and view all your options. If you double click on each one of those, it opens a tab that it will show you while your task is running in parallel. You can see how your resources are allocated, how your memory is used, and how many subtasks are defined. Like you can see how many total tasks you have and how this is being progressed. I also recorded my screen while I ran that, and I included that in our Google Drive. If that helps, you can also access it through this link. And let's talk about when does parallel processing work well. As a scientist, we experience times that our computer is able to handle the processing that we do, but it takes a really long time. So in that case, we don't really need anything externally to enable us to run the task, but parallel processing will be able to help us to make this process faster by allocating more resources to analysis. There are some other times that we do have our memory issue. So our computing processes are limited to the hard disk and a RAM that we have. And if, let's say, we are accessing a very large file and our computer is not, and when we are using Python or R to load that data in, we don't have enough RAM. So in that case, you can utilize the chunking, available chunking, which we can talk about. We will talk about that later. And you can distribute the computation resources you have. You can use the parallel processing to speed up your request. And that's a great example of a time that you can benefit from parallel computing. But the parallel computer will not resolve all the issues we have. Sometimes the computer that we are working with, it does not have enough resources for what we need to do. And that's where you need to think about maybe moving to the cloud, maybe changing your workflow and rethink your workflow. But even when you think about moving in a cloud, it's good to think about how you can have efficient workflow and how you can benefit from all that is available in that workflow that you have and leverage those resources. We talked about chunking, but what is chunking? So if you're familiar with the X-array, that's a Python library that we work to access multi-dimensional data assets that we have. And it integrates with DAAC that enables us and support the parallel processing. So the X-array allows us to define a chunk size. Basically, the chunk size, it's when you have a chunk size, you have a snapshot of a data, and and that data is available as a metadata in your system. So you are making the process in a way that is a lot more efficient to work with a multidimensional data in Python. And if you look at this screenshot here, so you have a data set, you're accessing a data set by variable, and each variable, it does have an array that use, let's say in this case, 4.8 gigabytes of your memory. If you imagine this data array is something like this, sometimes you don't need the entire data from an entire file. You just want to access a smaller subset. So chunking will enable us to be able to access the part of the data that we are interested in more efficiently. It does not load the entire file. It does have information about each one of these chunks and where the data actually is. And if you want to access that data, it will only grab what you need. So, which makes it very, very efficient in terms of using your memory. So technically, it shows where the subarrays are for your data. And let's talk about how you can get started with the parallel processing. So it would be good to know what your computer is capable of doing, to know how many CPUs you have, how many cores you have, what is your free memory in hard disk, what's your available RAM, and have a realistic estimate of how much memory your data storage and processes need. It's good to know that all the data formats that we are working with, NetCDF4, HDF file, COG file, they all store compressed in a ways. So when you look at the metadata to see how much space or memory that data needs, it might not be a realistic estimation of how much data consumes when we open the data in R or Python. So I provided an example. So in this example, one of the NetCDF file that we were working with uses 1.3 gigabytes. But when we only read one data variable using Xarray, that consumes 4.8 gigabytes of the memory. And this is the benefit of chunking, because that chunks are consuming less memory and makes the process even more efficient for us. And then it's good to consider working with a smaller sample of a data. That might sound like a common sense, but it's good also to emphasize that it's good to troubleshoot, make sure your code does what you intended to do, and troubleshoot, do a try and error. You can kind of work with different chunk sizes, work with allocate different number of cores to your process to kind of find the ways that your workflow won't fail. And if you are working with a 2I2C instance, we have a luxury of always increasing the memory that we are working with in case of the failure, that you can really benefit from. And there are ways, I know that there are ways in DAAC that you can shut down or quit your workflow. But in my experience, if you run a very, very big job, you might not be able to stop it. So think and troubleshoot and make sure the workflow is you don't need to do any more updating your code, and then let the things run. And yeah, thank you for listening to me. I included a few codes from our mentors in here that it's good to hear. So just know it does not work the first time. It always fails the first time. It does not, parallel processing doesn't resolve all the issues. Sometimes we need to add that to other things like migrating to the cloud or using a supercomputer or something like that. And when you think about moving your workflow to the cloud, don't think that you need to, it's not just copying and pasting your notebook or your data in the cloud. It's good to think that there are more resources available to me. So how can I benefit from those computational resources to make my process efficient and faster?